Welcome, Mike here. We're going to talk about random variables, and we call that turning letters into numbers. We've talked about things like P of A, P of B given A and B are events. We now want to talk about the concept of random variables. And a random variable simply is a variable that takes on different values with different probabilities. That's what makes it random. We know what the outcomes are, we just don't know which outcome occurs in any instance. So a random variable takes on different values with different probabilities. Now, they're discrete random variables. They can only take on a few values, and continuous random variables can take on any one of an infinite set of values. We add discrete random variables, so to work with discrete random variables, you have to be able to add. To work with continuous random variables, big time, you need to be able to do calculus, because you have to find areas under curves. We just work with a few special continuous random variables, so we don't require calculus, but be aware, if you're going to do a lot of probability theory and study a lot of continuous random variables, you have to brush up on your calculus. Some examples, and we always use capital letters to denote discrete random variables in general. So stock 50 Christmas trees, number of Christmas trees sold. You could sell 0, 1, 2, 3, 4 up to 50. X is number of trees sold. Percent of building completed after 4 months. Our random variable R denotes the percent of the building completed after 4 months. So this is a continuous because it's sort of in an interval there. These are all discrete random variables. And we just use capital letters to denote random variables. And you can always convert things into random variables. And it's up to you to decide how you want to code things. So here, response to a questionnaire, and we define a random variable to be the numbers 1, 2, 3, 4, 5. We might define a random variable to be 0, 1. Here's a random variable defined to be 1, 2, 3. It's up to the user of probability how they want to define their random variable. Now, a little notation, and it won't make sense until we start doing this. Capital letters are random variables. Little letters represent the values they take on. So capital letters are random variables. Little letters are the values they take on. And before we even begin, let's show you the interplay between data and random variables. So data is produced from random variables. So there's a strong relationship between them. So data has a histogram, random variables have a distribution. Data have a mean x bar, random variables have what's called an expected value E of x. Data has a variance, called s squared. Random variables have something called a var x. And we'll see more about all these formulas in just a little bit. Going back to that big X and little x notation, we call this the probability mass function of a discrete random variable, and it's simply the probability the random variable takes on a value. So over here's the random variable, and here's the values. This is saying, what's the probability the random variable equals the little value x? And it's defined for any value we put in. So you can say P of 1 was the probability if you roll a 6-sided die, you get a 1. 1 over 6, the probability you roll a 6-sided die and get a 2. 1 over 6. What's P of 17? It's not undefined. It's either going to be 0 or some non-zero value. When you roll a 6-sided die, the probability of getting a 17 is, of course, going to be 0. So easy to find here. The requirements for a random variable are the basic axioms of probability. Probabilities have to be between 0 and 1. And if you sum up all the values a random variable can take on, it has to sum to 1. So your basic ideas of probability theory. As an example, random variables are often shown in a probability table, discrete random variables that is. This is number of people in an American household, 1, 2, 3, 4, 5, 6, up to 7. If we add these probabilities together, you'd see they add up to 1. And then a question would be, what's the most likely number of people in a household? Just where is probability the highest? And that would be 2. What's the probability of a household having fewer than 4 people? How can you have fewer than 4 people? You can have 1, 2, 3. So you'd add up 0.23 plus 0.31 to 0.18. According to this table, what's the probability of a household having more than 7 people in it? It'd be 0. It doesn't occur in this table. Here's a graph of what's called the probability mass function, and sometimes we draw things like this. We don't ever want to connect the dots, even though you have a huge urge to connect the dots. We don't connect the dots because that gives you an idea that, hey, there are values in between. And it's discrete random variable. It only takes values. We'd say it has mass at just a few discrete points. So we never want to connect the dots here. And as an example, this is the machine breakdowns and the cost of a breakdown. There's a 30% chance the breakdown costs 50, a 20% chance it costs 200, 50% chance it costs 350. Again, these sum to 1. And then that's a graph of the probability mass function. You can define what's called a cumulative distribution function. It's often abbreviated CDF, cumulative distribution function, and it's simply this, and we'll see it again, the probability you're less than or equal to some value. For discrete random variables, it has a stair-step type approach to it, and it's simply cumulative probability, and it always asymptotes, always maxes out at 1 over here. As some practice, and you can see these questions are not difficult, random variable has the following probability distribution function. What's the value of the constant c? Well, we know 3c plus 7c plus 0.4 plus 0.1. Let's get a point in there. That has to equal 1. So 10c plus 0.5 equals 1. So it's got to be 10c plus point. No one said it would be math today. It's got to be D, I think. That's the right answer. Which of the following are legal probability distributions? Well, you know, probabilities can't be negative, and they can't sum to bigger than 1 or less than 1. So 5, 7, 8. This one's bad. This one's negative. That's bad. This one's more than 1. This is just like Goldilocks, just right. That's a good one. Now, as an example, here's the Pick 3 lottery from the Georgia Lottery. You pick a 3-digit number. So there's 3 digits here. You pick a 3-digit number. And it can go all the way from 000 to 999. And there are 1,000 different possibilities. So there are 1,000 numbers here. And you pick one. So the probability you win is 1 over 1,000. And the probability you lose is 999 over 1,000. And we could say W is our net gain. It costs $1 to play. If you win 500. You get 500 back. So if you lose, your net gain's -1. If you win, you get 500 back. It costs you $1. Your net gain's 499. So you might define a random variable where you win 499 with probability 1 over 1,000. You lose -1 with probability 999 over 1,000. Much greater chance you're going to lose than you're going to win. And much like a data set, when we want to talk about the mean and variance of a data set, we can talk about the mean and variance of a random variable. And so the mean of a random variable is defined by this. It's often given by the Greek letter mu. And it just says value times probability, value times probability, value times probability. So it's just a weighted sum of the different values the random variable can take on. And it should look very similar to the mean of a data set. Mean of a data set looks like this. We change the weights to how often the values occur, and this is the mean of a random variable. Straightforward to do for the Pick 3 lottery, value times probability, and this is the outcome. Now, you can't ever win minus 0.5. On any one game, you're either going to win $1 or lose $1. So where does this minus 0.5 come into play? That would be the long run average. If every day you played the lottery and you wrote down your winnings, you'd write down a lot of -1s. But occasionally you'd have a 499. So if you averaged over all those days, on average it's a minus 0.5. That's the average winnings when you play the Georgia Lottery, which is not really average winnings, but it's what the state makes from you. You're not winning money. It's a negative expected value game, we'd say. So negative expected value games are better for the other side. Positive expected value games are better for you. And then if the expected value is 0, that's considered a fair game. So in the long run, we lose 50 cents for every time we play. And the state makes 50 cents on average for every player that plays the game. Now, as an example, what's the expected value when you roll a fair 6-sided die? The answer is 3.5, but it's 1 times 1 over 6, plus 2 times 1 over 6, plus 3 times 1 over 6, plus 4, plus 5, plus 6. And if you actually do it out, you get a 3.5. Plus ... It's going to be a 3.5. As another example, suppose it's insurance. Suppose you're working for an insurance company, and these are your probability of losses on writing a policy. There's an 80% chance that you're going to pay out nothing, a 10% chance you're going to pay out 1,000, a 5% chance you're going to pay out 5,000, 3% chance you're going to pay out $10,000, and a 2% chance you're going to pay out 15,000. What should they charge if they want to make on average $100 per policy? So on average, they want to make $100 per policy. Well, the expected value times probability, value times probability, value times probability is 950. 80% of the time, they'll pay out nothing. 2% of the time, they'll pay out $15,000. The average payout's 950. Well, if they want to make, on average, $100, then they'll charge the customer $10.50. 80% of the time, they get to keep all that. 80% of the time, they get to keep the $10.50. 2% of the time, well, they're paid $10.50, but they have to pay out $15,000. So 2% of the time, they're out $14,000. But the math shows the expected value is $9.50. So if they charge $10.50, on average, they'll make $100 per policy. Here's another formula exam question. And here, we just want you to set up the expected value and solve for the constant C. If you want to try it and see if your answer is right, send me an email and I'll let you know. Some rules of expected value. Well, the expected value of a constant times x is the constant times the expected value of x. Expected values work really nicely. The expected value of x plus a constant, the expected value of x plus a constant, and then this is a nice rule that we use a lot of. The expected value of the expected values. And we didn't turn off notifications. That's great. So that's what's going on with expected values. Now, one more example before we move on to something called variability. Consider the following bets. You get $5 with probability 1. You get $10 with probability 0.5, 0 with probability 0.5, so on and so forth. Which bet's the best bet? Well, bet A has no risk whatsoever. You always get $5. Bet D has big outcomes there. What's the expected value? Well, each bet turns out to have expected value of 5. So on average, each bet's the same, but which one's the safest and which one's the riskiest? Well, we know about variance of a data set, how spread out a data set is. We need to discuss variance of a random variable. So for the betting example, each bet has an expected value of 5. And you should be able to show that. But one question is, and we're not going to see it on next week's homework, but one question is, what's the variability? And which one's the safest? Which one's the riskiest? This is clearly the safest. There's no downside risk for you whatsoever. 100% chance you're going to be paid $5. But the other ones varies a bit. The variance of a random variable is given by this, and it's very similar to the variance of a data set. And we call sigma squared the variance of a random variable. We take the square root of that to get standard deviation, of course. And, all right, the formula looks weird, but it's very similar to if we had data. If we had data be 1 over n minus 1, xi minus x bar squared. Now we don't have an x bar, we have a mu. And we don't have a 1 over n minus 1, we have probabilities. So it's a weighted sum of these deviations from the mean squared. Similar, yet different, still a pain in the butt to calculate. But it's the variance of a random variable. So the pick 3 game is just a lot of bookkeeping. Remember this game, the mean was minus 0.5, value minus 0.5, value minus the mean squared, that's mu. Value minus mean squared times probability, value minus mean squared times probability. This is dollar squared because it's variance. Take the square root, you get 15.8. Why is the standard deviation so much larger than the mean? Because it's a big spread. The only outcomes are 499 and minus 1. So there's a huge spread between them, and that's what that huge standard deviation is showing you. It's a big spread between the outcomes. For the insurance example, the variance is a huge number, 7 million. You take the square root, and you get 2018. And again, the mean was 950. The standard deviation is not that large relative to the mean because the values are not spread out that much. But it just says, standard deviation, of course, is saying how spread out are the values. Another way of calculating variance, this is sometimes called the shortcut formula, is E of x squared minus the mean quantity squared. It gives you the exact same formula for the exact same value for the variance. It just is sometimes an easier formula to calculate. As an example, suppose you pay $6 to pick a card from a standard 52 card deck. If the card's a diamond, you get 22. If the card's a heart, you get 6. Otherwise, you get nothing. What's the expected value and variance of this game? Here's the table set up. So if it's a spade, it's minus 6, heart 0, club minus 6, and diamond 16. Well, the probabilities work out to be this. And now, if you want the expected value, it's simply going to be value times probability. So minus 6 times 0.5 plus 0, we don't worry about 0.25, plus 16 times 0.25. If you work that out, you get the expected value. Now, how do you figure out the expected value of x squared? You simply square the x's. So it's going to be 36 times 0.5 plus 0 squared. Let's forget that. 0 squared plus 16 squared times 0.25. So you work that out. That gets you E of x squared. And then you can use the formula to find the variance of the data set. Again, email if you want to check your work on this. And we have the exact same slide twice, no clue why. Some basic rules of variance. Variance works a little bit differently than expected value. The variance of x plus c is the variance of x. Shifting something over by c does not change the variance. Variance is all relative to the mean. And if you shift everything over by a constant, the mean is shifted over by a constant. So shifting does not affect variance. Multiplication does. So the variance of a constant times a random variable is the constant squared times the variance of the random variable. And then more importantly, this is a big deal. Move that over there. Unlike means, the variance of a sum in general is not the sum of the variances. For means, this is true. For variances, this is not true in general. And you want to keep that in mind. And we'll talk more about that as we get deeper into the course. As an example, here's a basic probability table. Profit of a random variable, different probabilities. Again, these have to sum to 1 to be legal. You can easily find E of x. You can easily find E of x squared. That's literally the expected value of x squared, the squared values. And then using the shortcut formula, you can find the variance of x. So again, some rules for expected value and variance. The expected value of a plus bx is a plus b expected value of x. Everything works nicely for means. For variances, the variance of a plus bx is going to be b squared times the variance of x. Here, a and b are constants. So one final example from this, an author receives a fixed sum of $10,000 plus $1.50 for each copy of her book sold. We know the mean and variance for number of books that the author is going to sell. So payments, 10,000 plus 1.5x, where x is number of books sold. X is random, so payment's random. So we can talk about the expected value of payment, and we can talk about the variance of payment. And that just uses the rules for manipulating var of a plus bx and expected value of a plus bx. So things you should know is what's a random variable, what the probability function is, how you figure out the probability big X equals little x, the expected value of a random variable called mu, the variance of a random variable called sigma squared, square root of that's of course called sigma, and then how you manipulate random variables, what we call the a plus bx rule. Hope this helped a little bit, and can't wait to see everyone in class. Thank you.